Elon Musk's projected 6-month journey to Mars aboard Starship, powered by its 39 Raptor engines, is sparking debate and prompting NASA to consider alternative propulsion systems. The sheer length of this estimated journey is a significant point of discussion, highlighting the limitations of current chemical rocket technology. The extended travel time poses challenges, including prolonged exposure to the harsh conditions of space, impacting astronaut health and mission viability. NASA's announcement of a revolutionary new engine, powered by an advanced energy source, signals a critical response to the limitations of chemical propulsion in long-duration space travel. This new technology aims to drastically reduce the time it takes to reach Mars, potentially shortening the journey to just a few weeks or even a day. The need for faster and more efficient travel to Mars and other destinations in deep space is a key driver behind this research. This initiative emphasizes the critical need for innovative solutions to overcome the limitations of traditional propulsion methods and pave the way for sustained human exploration beyond Earth's orbit. The development of faster propulsion systems directly addresses the time constraints and risks associated with extended space missions. The potential breakthrough in propulsion technology could significantly impact the trajectory of human space exploration and potentially foster a new era of interplanetary travel. Concerns about the physical and psychological toll on astronauts during lengthy space voyages are prompting both SpaceX and NASA to seek more effective methods of travel. Chemical rockets, the bedrock of space exploration, rely on the combustion of propellants and oxidizers to generate thrust. These rockets are broadly categorized into solid fuel and liquid fuel types. Solid fuel rockets combine the propellant and oxidizer beforehand, while liquid fuel rockets store them separately, combining them on demand within the combustion chamber. This process creates high-temperature, high-pressure gas that is expelled through a nozzle, providing the thrust needed to propel spacecraft. SpaceX's Starship, a vanguard in deep space travel, utilizes a unique, full-flow staged combustion cycle engine, the Raptor, for its propulsion. Crucially, the Raptor departs from traditional designs by employing methane and liquid oxygen as fuel. This departure from kerosene or hydrogen fuels is a key innovation, focusing on superior fuel efficiency and a higher thrust-to-weight ratio. The Raptor engine's enhanced performance compared to conventional designs is a significant advancement, representing a shift in the technological approach to rocketry and propulsive capabilities. This advancement in fuel technology represents a significant leap forward in propulsive efficiency. The use of methane and liquid oxygen is not unprecedented in rocketry, but the Raptor engine's implementation demonstrates a focus on efficiency and potentially lower costs associated with these specific propellants. NASA's pursuit of advanced propulsion systems, specifically nuclear thermal propulsion (NTP), represents a significant departure from the established reliance on chemical rockets. NTP aims to drastically reduce the time required for deep space missions like those to Mars, potentially shortening travel durations to weeks or even days. This ambition stems from the recognized limitations of chemical propulsion, particularly concerning exhaust velocity and the extended travel times it necessitates. These limitations translate into significant challenges for astronaut health, radiation exposure, and mission complexity during long-duration interplanetary journeys. NTP, leveraging nuclear fission, promises dramatically higher energy output per unit of mass, thereby enabling faster acceleration and reduced travel times. The technology, though not entirely novel, faces challenges in terms of safety and scalability. This innovative approach to propulsion, offering substantial improvements in efficiency and travel speed, could revolutionize interplanetary travel. However, addressing the safety concerns and logistical challenges associated with nuclear propulsion systems is critical for the successful implementation of this technology. The potential advantages of nuclear propulsion, including reduced travel times and enhanced mission capability, are driving NASA's intensive research and development efforts. NASA's DRACO program, a crucial component in developing nuclear thermal propulsion, highlights the agency's commitment to groundbreaking propulsion technologies for deep space exploration. The program, a collaboration with General Atomics, aims to demonstrate the viability of nuclear propulsion for missions beyond low Earth orbit, particularly for voyages to Mars and beyond. The program's focus on highly enriched uranium (HEU) fuel was previously a significant concern due to proliferation risks. However, the program now focuses on a safer alternative, high-assay low-enriched uranium, HALEU, which minimizes those risks. This shift towards a safer fuel source is a pivotal aspect of the program's success and acceptance. This effort requires significant advancements in reactor design and fuel handling to ensure both performance and safety. The need to maintain reactor integrity throughout a mission while achieving high speeds is paramount. These challenges demand innovative solutions in materials science and engineering. The Draco program's initial focus is on establishing the basic feasibility and safety of nuclear propulsion for spaceflight applications. Success in the Draco program could significantly alter future space missions and open up new frontiers for deeper space exploration. The ongoing research and development efforts surrounding nuclear thermal propulsion highlight the multifaceted nature of the endeavor. Experiments conducted at the Idaho National Laboratory, in collaboration with NASA, are vital for refining materials suitable for use in nuclear reactors, which need to endure the intense heat and pressures of spaceflight. These efforts aim to validate theoretical models and improve the efficiency of the propulsion system. Scientists are working to find the optimal uranium-based materials and structures capable of withstanding the extreme conditions of a nuclear propulsion reactor. The research also focuses on optimizing the propellant, with hydrogen being a primary target due to its high specific impulse. However, the lower density of hydrogen presents logistical challenges, leading researchers to explore alternative propellants like ammonia, offering a trade-off between specific impulse and density. These ongoing research initiatives are key to overcoming the practical and technical hurdles associated with this potentially game-changing technology. The continued investment in research and development underlines the long-term commitment to advancing nuclear propulsion systems and paving the way for more efficient and ambitious space travel in the future. The ongoing research and development indicate a sustained effort to overcome the inherent challenges of utilizing nuclear power in space propulsion, ensuring its safety and effectiveness for future applications. The potential applications of nuclear propulsion extend far beyond interplanetary travel, encompassing crucial aspects of national security and commercial space operations. The ability to rapidly maneuver spacecraft within the cislunar space, the region between Earth and the Moon, holds strategic advantages, particularly for both defense and commercial applications. The potential for faster transit times and increased maneuverability within this region has significant implications for military and commercial satellite operations, as well as space resource extraction. The Draco program's focus on demonstrating nuclear propulsion's viability in low Earth orbit is a critical first step in assessing its applicability across a wider spectrum of space missions. This multifaceted approach, combining research, development, and potential applications across various sectors, highlights the growing importance of nuclear propulsion. The potential military applications of this technology, in addition to its commercial applications, emphasize the significant implications for national security and economic advancement in the space sector. The multifaceted approach, combining research, development, and potential applications across various sectors, highlights the far-reaching importance of nuclear propulsion for future space operations. The potential for military applications, alongside its wider implications for commercial and scientific missions, emphasizes the significant implications of this technology for the future of space travel. NASA and General Atomics test nuclear fuel for future Moon and Mars missions. The first humans to Mars might someday ride a rocket propelled by a nuclear reactor to their destination. But before that can happen, nuclear thermal propulsion, NTP technologies still have quite a way to go before we could blast astronauts through space on a nuclear rocket. However, earlier this month, General Atomics Electromagnetic Systems, GAEMS, in collaboration with NASA, achieved an important milestone on the road to using NTP rockets. At NASA's Marshall Space Flight Center in Alabama, General Atomics tested a new NTP reactor fuel to find out if the fuel could function in the extreme conditions of space. According to company leadership, the tests showed that the fuel can withstand the harsh conditions of spaceflight. We're very encouraged by the positive test results, proving the fuel can survive these operational conditions, moving us closer to realizing the potential of safe, reliable nuclear thermal propulsion for cislunar and deep space missions, General Atomics President Scott Forney said in a statement. To test the fuel, General Atomics took the samples and subjected them to 6 thermal cycles that used hot hydrogen to rapidly increase the temperature to 2600 degrees Kelvin or 4220 degrees Fahrenheit. Any nuclear thermal propulsion fuel aboard a spacecraft would have to be able to survive extreme temperatures and exposure to hot hydrogen gas. To test how the fuel could withstand these conditions, General Atomics conducted additional tests with varying protective features to get further data on how different material enhancements improve the performance of the fuel under conditions similar to that of a nuclear reactor. According to the company, these types of tests were a first. To the best of our knowledge, we are the first company to use the Compact Fuel Element Environmental Test (CFEET) facility at NASA MSFC to successfully test and demonstrate the survivability of fuel after thermal cycling in hydrogen representative temperatures and ramp rates. Christina Back, Vice President of General Atomics Nuclear Technologies and Materials, said in the same statement. NASA and General Atomics tested the fuel by exposing it to temperatures up to 3000 Kelvin, 4940 Fahrenheit, or 2727 Celsius, finding that it performed well even at temperatures that high. According to Back, this means an NTP system using the fuel could operate 2 to 3 times more efficiently than current rocket engines. One of the main reasons why NASA wants to build NTP rockets is that they could be much faster than the rockets we use today, which are propelled by traditional chemical fuel. A faster transit time could reduce risks for astronauts, as longer trips require more supplies and more robust systems to support the astronauts while they travel to their destination. There is also the issue of radiation. The longer astronauts are in space, the more cosmic radiation they are subjected to. Shorter flight times could reduce these risks, making the possibility of deep space human spaceflight closer to reality. In 2023, NASA and Defense Advanced Research Projects Agency DARPA announced they're working on a nuclear thermal rocket engine so that NASA can send a crewed spacecraft to Mars. The agency hopes to launch a demonstration as early as 2027.